I'm looking at the time over there. Good evening to the US. Good night almost to the US. A very early good morning to Europe. And good morning to Asia. I think Australia, New Zealand. And also good morning early to Africa. And good evening to South America. Um, we are live. Welcome, welcome, welcome to the live. Thank you for being here. If you're joining, as always, welcome, welcome. We will be covering Jovian planets. Finally, our dream is coming true. I know many of you have wanted, especially, to hear about Jupiter's moons, including but not limited, of course, to Europa, and we will start upon this particular topic today. So, we have been talking about the terrestrial planets in more detail over the course of the last few lives, including, of course, Venus, Mars, and in the last live, we covered Mercury. I almost said Mars, but we actually talked about the Earth and its moon. Of course, our moon we touched upon, and there are some kitty cats with their zoomies happening as well right now, so you might hear that in the background. Let me actually show you. Where is Baji? I know Suji Mama is here somewhere, and I think Fuji is having zoomies right now. So there is that. But yes, indeed, Fuji, indeed, we talked about. Oh, Fuji has brought me his nightly gift. Come, Fuji. Hi, Fuji. Thank you. Thank you, Fuji. So I have to accept the gift. Let me show you. So here's the blue gift. Here's the kitty cats. Hi, Suji, Mama. Hi. Oh, there is Baji. Hi, Baji. Hello. There's Baji, Fuji, and Suji. All right, everybody. Thank you. Thank you for joining. Welcome, welcome. In the last live, we took some time to talk about, of course, the smallest planet in the solar system, which is Mercury. We saw that it had very small mass, smaller than our moon, and we saw a number of rather interesting features of the planet. And we also got into Venus, but we had already covered Venus and Mars in a previous nightly live. So today we will get into the Jovian planets, but first I will actually share the live because I can see that it's a little bit quiet. Hopefully many of you will join very soon. Hello, welcome. Hello, hello, hello. Welcome. Thank you for being here. I'm looking at my channel on my Mac here. Welcome. Hello. So we always generally spend a little bit of time catching up with everybody and saying hi to everybody. Reese, hello. I think you like the live today, Reese. It's gonna be Jupiter. So it's gonna be the Jovian planets, and indeed we will talk about some things that we have mentioned in the past. Thank you for liking the live. Thank you for sending the hearts and emojis. Thank you so much. Reese, hello. Almanza, hola. Hi. Liam Montella says, can we get a fit check? Well, this is a dress from, I believe, Old Navy. JBBY, the boy 400 says, hello. As long as it's not the moon and the origin of craters. Yes, no, it's not gonna be our moon today. Reese sends an emoji. Nausat, hi, looking very beautiful. Thank you. Thank you so much, everybody. Like done. Yes, please do. If you could like, subscribe, that would be amazing. J.O. Hi. Message you. Well, I don't think there is such a thing on YouTube, thankfully. You are looking. Oh, thank you. If everybody is enough stunned. We will get started. We will get started. Hopefully, everyone feels stunned and ready for some planets today. What is this about? Just rolled in. So, thank you. Tribe of Reality. Hello. Latrell Trill Beats Richards. You are looking black today. Yes, I am wearing a black dress. Thank you. So, this is going to be about planets. Thank you. It's going to be about the planets we covered the terrestrial planets already. Today we will cover the Jovian planets, that is the Jupiter-like planets. So when we said terrestrial planets earlier, we meant the rocky planets, the metallic planets, like Earth has rock. Mercury, we found, has an enormous metallic core. Mars, we talked about as well, has a bunch of rust. Venus, we talked about as well, very much like the Earth in some ways, in size, mass, radius, sort of. Almost very close to Earth, almost a twin, but but has a very poisonous atmosphere due to lack of oceans on Venus, which could have absorbed the carbon dioxide, which could have then trapped it in limestone upon making calcium carbonate when carbon dioxide reacts with water and makes H plus and HCO3 minus. I wanted to make sure I got that right. So yes. Reese, thank you so much. Look at Reese, he's moderating. What is your name? So the channel name is Baji the Handsome Cat. We also have kitty cats here that I show, and I am their mother. So Baji's mom is my name. You look like a star up in the sky. Well, thank you. Latrell says, what about J1407b? Talk about mass. So what's up with the moon? Why don't it spin? Which moon are you talking about? It... So we actually covered some facts about the moon and especially how it got impact craters a couple of lives ago. This particular live even had us fighting a little bit, but that's all fun. That's all good now, and I think we are past that. You will also note that a lot of people in the last few lives talked about the moon landing. This is because we were talking about the terrestrial planets and their moons, and we mentioned, of course, Earth and our moon, which is also one of the biggest moons in the solar system. We also talked about Mercury and Venus, who don't have moons. And we also talked about Mars. And so now we're kind of done with the rocky terrestrial planets. And we're going to head off to start with the Jovian planets, which is, of course, Jupiter and beyond. I never shared the live, so I'll do that right now. We are live. Okay. So you know what? Without further ado, so yeah, I was real quick. I thought it was the most cool thing that carbon dioxide dissolves in water, where it forms among other compounds negatively charged bicarbonate ions. This is in respect to Venus, of course. So Venus has a bunch of carbon dioxide in its atmosphere. So, but if it had liquid water, like a bunch of oceans, like here on Earth, it could have done this CO2 plus H2O, giving us H plus HCO3 minus type of interaction. And the bicarbonate ions combine readily with any calcium ions dissolved in the water, which would then give us Ca2 plus plus 2HCO3 minus, giving us CO2 plus H2O plus CaCO3. And that calcium carbonate, because it's poorly soluble in water, it actually precipitates out to the ocean floor and is contributing to something like limestone. So basically it's one way to take the carbon dioxide out of the atmosphere and convert it to rock. And because we did that on Earth, here we are. We have less carbon dioxide and more of this breathable air that we are lucky to have. Today, what is special? Nothing special. I just thought I'll try out a little lipstick. That's all. I didn't do anything else specially. I just put on a dress and put on this lipstick. That's all. Everything else is the same. Hello. Hello, Rodolfo. Hello, Nausad. Hello, Tribe of Reality. Hello, Space Cowboy. Hello, Latrell. Hello, Reese, of course. Thank you so much for coming. Hello, Stephen. Hello, Crazy Paul. Hello, Nausad. Okay, so I think I've said hello to pretty much everybody. Stones Avengers. Okay, I don't know what that is, but okay. So by the way, we have been, of course, referencing this book. This is called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. We have been using this book a lot. It has a lot of really good astronomy lessons. It is used as the textbook for astronomy majors. I believe it's for undergrads, but I may be wrong. It may also be used for part of the grad program in astronomy departments in university. So that's what we're referencing. And these authors, thankfully, I actually know them because I also worked with them. And I got this book for free. So thank you to the authors, Barbara and Bradley. And they were also, I was a TA in the Department of Astronomy at one point, so I had to have this book. So there we go. So now that we have said all these things, we will go to the Jovian planets. Now, sometimes I do these lives with just my voice and showing the kitty cats, but a TA is a teaching assistant ship. So sometimes in graduate school, when you're doing your PhD, you might have, there's a couple different ways of getting paid. Like, so if your tuition could be awarded as part of a sort of a scholarship, and then you might get paid a stipend, either by doing a teaching assistantship or a research assistantship. So that's what a TA is. So when, say, if you're not getting paid out of research grants because you're still sort of a more junior grad student, you might have to do a teaching assistantship. Sometimes you could be a senior grad student and simply there could be something off with the research grants and you might have to do a teaching assistantship again. So I gained a lot of teaching experience by doing all of this in academia, which was nice because taught a lot of people, a lot of students, a lot of diversity of people and backgrounds. I did teacher's assistant my senior year in high school. It was interesting. Oh, yes. So I think throughout academia, pretty much even in undergrad, in college, in grad school, you might end up with something like that, some sort of arrangement like that, where you get basically a teaching assistantship as part of is part of your gig, basically. But it's incredibly common, especially in the grad programs. So that's what that is, and that's how I've gained so many books. Some of them are from my own classes when I was a student, and some of them are from my teaching assistantship type of experiences, helping the professors with their classes and things like that. So coming to the Jovian planets. So what we mean by the Jovian planets are, of course, Jupiter-like planets. So we are now leaving the proximity area from the sun, like things like Mercury, Venus, Earth, and Mars, and going even more farther out into the solar system. And we're starting with these Jupiter-like planets. So we have, in order of increasing distance from the sun, our Jupiter, which is at 5.2 AU, or astronomical units. So I mentioned yesterday that an astronomical unit is basically the distance between Earth and the sun. In astronomy, many things are basically given in terms of, say, for stars, it is given in terms of our sun. So a star's mass might be given in terms of the solar mass or our sun's mass. The distance between different objects might be given by, in reference to the distance between the Earth and the sun, or an astronomical unit of distance, or 1 AU. So this is very common. So we actually looked at it, and we know that Mars is at 1.52 AU. That is the farthest rocky planet from the sun. And as you can see, then there's a big gap. Without any planets, there's some other stuff we'll get into, but without any planets, and then you have Jupiter at 5.2 AU, 5.2 astronomical units. So that is 5 times the distance between us and the sun, Earth and the sun. So everything is kind of given in these other units that are hopefully kind of relatable. So you might hear something like the mass of the Earth, M Earth, or mass of the sun, M Sun. Stars masses might be sometimes given in terms of the M Sun. Planet masses might be sometimes given in terms of M Earth. And distances are often given in terms of this astronomical unit, or AU, 1 AU being the distance between Earth and sun. Okay? Asteroid belt. Yes. Hi, Griffin. Hi, Crazy Paul. Okay, so then we have Jupiter at 5.2 AU, Saturn at 9.6 AU, and Uranus at 19.2 AU, Neptune at 30 AU. These are 30 AU, 30 astronomical units. So that is really far away from the sun. Very far. Neptune is very far. In order of decreasing mass, so from biggest mass to smallest mass, we have Jupiter at 318 M Earth. That is 318 times the mass of the Earth. 318 times bigger in mass than the Earth is Jupiter, the largest planet in our solar system. Then we have Saturn at 95 M Earth, Neptune at 17.1 M Earth, and Uranus at 14.5 M Earth. That could be. That very well could be. And then did I say Uranus at 14.5 M Earth? There are many properties that the Jovian planets have in common. They're all massive bodies that formed far from the young sun, where the temperatures were low enough to allow condensation of volatile ices as well as refractory rocks and metals. So we actually talked about condensation, I think it was a few lives ago, where we basically talked about the formation of our solar system. I believe the asteroid belt was once a failed planet. That very well could be. Yeah. You're a science teacher. Thank you. Activated. Yay. So we talked about how our solar system was probably this massive, giant gas cloud that started to condensate. And of course, we actually looked at a picture of it too. Of course, the biggest sort of thing is the sun, and then the planets also started to form as a result of certain condensation. And depending on what things condensate, C-O-N-D-E-N-S-A-T-E, condensate, at what temperatures you will have a planet of that material basically at a certain distance from the sun, because of course, if you're farther from the sun, you're going to be very much cooler. Saturn is a squared. What do you mean by squared? Gas giant, not fully round like Jupiter. Neelam squashed. Oh, squashed. Yes, we'll get there. We will get to Saturn. So basically there are many properties because, as you can see, these planets are so much farther away from the sun than the rocky planets. Now, of course, Jupiter being at 5.2 AU is still a lot closer than Neptune, which is at 30 AU, right? Because Neptune is like another 6 times farther away than Jupiter. And of course, also we saw that the mass of Jupiter is the biggest one. Jupiter, again, 318 M Earth, Saturn 95 M Earth, Neptune 17 M Earth, Uranus around 14 M Earth. So this mass will also play a very big role, as we will see. There are many properties that the Jovian planets have in common. They're all massive bodies, so much, much bigger. That's one thing. That formed far from the young sun, far from the young sun. So when the sun had also recently formed, where the temperatures were low enough to allow condensation of volatile ices, as well as refractory rocks and metals. So these materials condensate at a lower temperature than some other materials, as we saw, which make up our terrestrial planets. The Jovian planets all have strong magnetic fields since they're rapid rotators and contain large amounts of electrically conducting fluids in their interiors. So this is another big one. They're all rapid rotators. So this is, compare this to what we learned about with, for example, the terrestrial planets. Some of them are very slow rotators, such as Venus, I believe, was the slowest rotator. Indeed, it was. And Mercury also was kind of very slow. We actually talked at length about how that affects their, orbital period versus sidereal period and things like that, and how there are some interesting relationships between those periods in the case of the terrestrial planets. But now we're doing the Jovian planets, and they are very, very different. Ben, hi, Ben, how are you? Checking in, good job. Oh, whoops, I touched the screen by mistake. I was trying to scroll up. Venkata, hi Venkata. Imagine if you're in a large ocean where Saturn is floating around. You mean you're Saturn? What we learned. Yeah, so these things are actually the Jovian planets are very rapid rotators, and as we know, that means that they're going to have strong magnetic fields. And they contain large amounts of electrically conducting fluids in their interiors. So if those things, remember, a changing electric field can cause a magnetic field. So of course, if you have something in the nature of electrically conducting fluids in their interiors, and we'll see what else they're made of course, and they're rotating rapidly, they will create a strong magnetic field. So these Jovian planets do. Oh, where are you from? Jamaica. Good job, Reese. They all have multiple satellites. So this is another big difference between the rocky planets or the terrestrial planets and the Jovian planets. The rocky planets, some of them don't even have moons, such as Mercury and Venus. Earth has one moon. We just have the one, right? So kind of special in that sense. I think we are the only planet, if I'm not mistaken, with just the one moon, because even Mars has more than one, and some of them have none when it comes to the terrestrial planets. But look at these Jovian planets; they have multiple satellites. Another very big difference. So the Jovian planets really belong to their own sort of very different class of planets within our same solar system. Are you in uni? I'm here to learn. I love astronomy. Thank you. Are we learning about the moon tonight? No, we're going to learn about the about the Jovian planets. She's a comedian and she doesn't know it. It is true, I am a comedian. Our moon is, Earth is the only planet with one moon. Exactly. Yeah, good job. Very good job. So they all have multiple satellites, the Jovian planets, the largest of which formed simultaneously with their parent planet, and they all have ring systems, of which Saturn's is by far the most spectacular. So as you know, we associate the ring with Saturn, but they all have ring systems. We will get into it in more detail later on. But Saturn's is, of course, the most spectacular. However, as a group portrait of the Jovian planet indicates, we can look at it later, there are some significant differences between the inner Jovian planets, Jupiter and Saturn, and the outer Jovian planets, Uranus and Neptune. So as you know, Jupiter and Saturn, as we can see, because these are at 5.2 AU and 9.6 AU. So within 10 astronomical units distance from the sun, we have Jupiter and Saturn, whereas Uranus and Neptune are much farther away. Uranus is at almost 20 AU and Neptune is at 30 astronomical units distance from the sun. So it's almost like even within the Jovian planets, there is Jupiter and Saturn are kind of like friends, and Uranus and Neptune are kind of like friends. So Jupiter and Saturn are large in both mass and radius. So the masses are over 95 m Earth, or the mass of the Earth, and the radii are around 10 Earth radius, our Earth. Compared to the relatively petite Uranus and Neptune, with mass less than 18 m Earth and radius around 4 our Earth, or radius of the Earth. Their colors at visible wavelengths. So remember, you can see light, you can have light in different wavelengths, visible and otherwise. But so these planets' colors at visible wavelengths are also quite different. The blue-green color of Uranus and Neptune results from methane. The brown and gold colors seen in Jupiter and Saturn are the result of trace amounts of complex compounds in their clouds. So we will get into more details, but basically just the colors and the wavelengths of light from these planets too, which manifests as the color, also gives away sort of something about their makeup. So again, blue-green color of Uranus and Neptune results from methane. Brown and gold colors seen in Jupiter and Saturn are the result of trace amounts of complex compounds in their clouds. The readily visible differences between the Jupiter-Saturn pair and the Uranus-Neptune pair are accompanied by differences in their internal structure. So there's differences in the internal structure as well. So size, distance from sun, the radius, the mass, the composition, the color. There's sort of these differences between the two pairs, Jupiter, Saturn, and Uranus, Neptune. As a consequence, we will find it useful to first investigate Jupiter and Saturn, and then we will talk about Uranus and Neptune. Chariots of the gods. Is there anyone who is thinking that our gods are aliens that visited our planet before? Yeah, I mean, you can still share about your ancient history knowledge if you'd like. That's totally welcome. I'm the alien that rules over your planet. So yeah, Venkata, if you'd like to talk about the planets in an ancient, astrology kind of way, then you're most welcome. I know that they're relevant in other fields as well. Every so often we have two moons, when a smaller moon appears for 2 months at night, like it did in October last year. So, so to recap, Jupiter and Saturn are kind of like a pair, and Uranus and Neptune are kind of like another pair. And these pairs are quite different from each other in mass, radius, distance from Sun, makeup, composition, all of that. So now we will get into a little bit about these particular planets. So one thing, keep in mind that Jupiter and Saturn are a lot bigger. Okay, so they're all bigger than Earth by a lot, but Jupiter and Saturn are a lot bigger. Okay, again, Jupiter mass is 318 m Earth, Saturn mass is 95 m Earth. So those are a lot bigger. And then we have Neptune and Uranus, which are more like 17 m Earth and 14 m Earth. So in the teen of m Earth. So we will look at these in more detail now. And I will actually summarize for you because we won't get into some of the more complicated parts and maths too much today. So that's in terms of radius, yes. In terms of radius, the radius of Jupiter and Saturn are around 10 Earth radii. But in terms of mass, it's an even more dramatic number. You know how you can have a lot more mass and the radius can be not as much larger? So that's the case here. The mass of Jupiter and Saturn are actually a lot bigger than the mass of Earth. But the radius, as you said, is around 10 Earth radius. Because there's also, things can also compress under gravity. So we will now look at this whole thing in a little bit more detail. We will get into it. So we will talk about Jupiter and Saturn. Then we will talk about satellites of Jupiter and Saturn. These will be really interesting. So there is a lot of details about Jupiter and Saturn in terms of the objects, Jupiter and Saturn, because the environments of Jupiter and Saturn are going to be very interesting and different than the environments of Uranus and Neptune. Because as we know, Jupiter and Saturn, already we know that they have enormous masses. They're much bigger than anything else. And so their stuff that's going on, the pressure and all of that is going to be very different. And there's a lot of details about that in this chapter. So we will cover that sort of in a summarized way. And then we will talk about the satellites of Jupiter and Saturn. Again, those are also a very important topic. And then we will move on to Uranus and Neptune. Okay? So that's sort of the itinerary of today. Let me just, yes. So there's going to be a little bit of math in the section for Jupiter and Saturn because I want to tell you about the I want to talk a little bit about the pressures inside these planets, okay? So it's not going to be completely math free, so just get ready. And then the satellites of Jupiter and Saturn are going to be very good stories because, as you know, they have very interesting satellites and a lot of current research a lot of current research is ongoing on the satellites of these bigger planets, bigger Jovian planets. So that's why we will definitely take the time to cover these. Okay, so the Jovian planets, let me take another sip. You said, okay, I see some people are fighting in the chat, but that's okay. Carry on and I will read your messages maybe in between. Thank you for being here. Thank you for joining the live. Okay, so the Jovian planets, like the terrestrial planets, have interiors that are in hydrostatic equilibrium. So the pressure gradient in their interiors must be given by the equation of hydrostatic equilibrium. Thank you. Yes, please do like the stream. I have 9 likes. If we could get 20 likes, that would be amazing. And let's not call each other any names in the live chat. We want everybody to be comfortable and mostly happy. Thank you for liking the live. Thank you for being here. Thank you for joining very much. So now we will talk about hydrostatic equilibrium. In the like. Yes. I'm behaving. Oh, good. Stephen is always behaving. Usually Stephen is never a bad boy in this live. So what we mean by this hydrostatic equilibrium, we will talk about, and basically pressure gradient, right? So this is going to be change in pressure with respect to radius, right? So it's in the calculus way, this is dp dr. So if something changes as a function of time, you might say something like velocity is dx dt. So the position changing as a function of time. So if something changes as a function of time, again, we can take the derivative of position, such as dx dt, where x is position, that's velocity. In this case, we're going to look at pressure gradient, which is given by dp dr. So dp dr is going to be minus gmr rho over r squared, where mr is the mass inside the radius r. So that's what we're going to be considering. It could be some mass of Jupiter, some mass of Saturn. We're now considering this type of thing for both Jupiter and Saturn. And this mass is inside the radius of r. We can take a big old integral and get that mr is 4 pi. And the integral goes from 0 to r. So from the 0 position to the radius r position, rho of r squared dr. So we have assumed in the above equations that we just mentioned that the planets are spherical. This is a good first approximation. So we're just trying to get a sense of the math of this stuff, of the pressure and whatnot in these planets. So although this is not strictly true, especially for the rapidly rotating Jovian planets, they're not totally spherical, but still. So we need to know the density profile of, so we're trying to get some sense of the density profile or the pressures and things going on within these enormous and very, very massive planets. So that's what all of this is about. So we want a rough estimate of the central pressure of the planet. We can make the rough approximation. When we want rough estimates of something, we can make a rough approximation that the planet's density is constant, as in rho of r is equal to rho. And with this assumption, the enclosed mass is going to be, when you put that rho in that integral that I just mentioned, you get 4 pi over 3 rho r squared. And the equation of hydrostatic equilibrium can be written as dp equal to minus 4 pi over 3 rho squared gr dr. So all of this, you integrate this equation, you do all this stuff. For Jupiter, this rho turns out to be around 0.24 the rho of Earth. And r is around 11.2 the r of Earth, so the radius of Earth. The estimated central pressure for Jupiter then turns out to be 1 times 10 to the 12 Newton per meter squared. So pressure is given, of course, as a force over an area. So Newton is the unit of force, meter squared is the area. So it turns out that Jupiter has a lot of pressure, a lot of pressure. So, and this is the central pressure that we have just computed for Jupiter with certain approximations in place, but we wanted to have an idea for the central pressure in Jupiter. And it turns out it is 1 times 10 to the 12 Newton per meter squared, which is around 10 to the 7 atmospheres. And as we know, the atmosphere on Earth at sea level is 1 atmosphere. So it's an enormous pressure in the center of Jupiter. Compared with Jupiter, Saturn is lower in density with a rho of 0.125 of rho Earth, and smaller in radius. So the Saturn planet is not as big as Jupiter in radius, but similar. So the R for Saturn is 9.45, the R of Earth. So 9.45 R Earth. So 9.45 times the radius of Earth is Saturn. Thus, Saturn's central pressure is smaller because we plug it into the things we did earlier. And it is 2 times 10 to the 11 Newton per meter squared, which is 2 times 10 to the 6 atmospheres, which is still a lot. So compare 10 to the 7 atmospheres and 2 times 10 to the 6 atmospheres as the central pressures of these planets, Jupiter and Saturn, the Jovian planets, humongous planets, massive planets, that are, of course, closest to the Earth amongst the Jovian planets. Enormous central pressure. Again, 10 to the 7 atmospheres and 2 times 10 to the 6 atmospheres compared to 1 atmosphere of us on Earth at sea level. Very different. So just keep this in mind and recognize that things are going to be very different in Jupiter. Materials and the pressures and the things that happens to those materials, this is not an Earth-like environment. It's a very different environment. Okay? At a pressure of millions of atmospheres, so this is 10 to the 6. Now, Stephen, how many zeros are in a million? Stephen will tell us. So, a million is 6 zeros, right? Good. Yes. Stephen is a good listener, so I'm going to ask Stephen the questions. If Jupiter has a central pressure of 10 to the 7 atmospheres and Saturn has a central pressure of 2 times 10 to the 6 atmosphere, that is basically millions of pressure or millions of atmospheres in pressure, right? So this is not, again, a normal kind of environment. What happens to different elements and different materials in this type of environment is going to be different, and there is a phase diagram here that I can show you in a bit. And basically this phase diagram will tell you what will happen to which type of thing in Jupiter and Saturn. Basically in this phase diagram, we have temperature on the y-axis in kelvins and pressure on the x-axis in megabars, another unit of pressure. So but the basic concept here is at a pressure of millions of atmospheres, hydrogen becomes a metal. A metallic substance is one in which a regular lattice-like structure of positive ions is surrounded by a cloud of delocalized electrons not bound to any particular atomic nucleus. So isn't that an interesting definition of a metal? Exactly. So basically, what is a metal, right? Like when we think about a metal, we might think of, oh, gold or silver or, iron. We have certain, we have a certain picture or a certain feeling in mind when we think about a metal. But actually, the definition of a metal is the following. Again, a metallic substance is one in which a regular lattice-like structure So there's a lattice of structure which is made up of positive ions, and they're basically surrounded by a cloud of delocalized electrons, where the electrons almost belong to this lattice and not bound to any particular atomic nucleus. Yes, the delocalized electrons, because remember, metals have to be good conductors of electricity, right? And what does that mean? Which means that electrons flow well, freely, goodly, whatever you want to say, within a metal, The delocalized electrons, called conduction electrons, are what give metals their characteristic properties, which is to, one of the biggest ones is, of course, to be conducting. So once again, a metallic substance is one in which a regular lattice-like structure of positive ions is surrounded by a cloud of delocalized electrons not bound to any particular atomic nucleus. The delocalized electrons, called conduction electrons, are what give metals their characteristic properties. Metals typically are reflective, are good conductors of heat, and are good conductors of electricity. So not just good conductors of electricity, metals are also good conductors of heat. It's like quicksilver and methane, a normal gas here on Earth. Venkata, you consult too much. Could you define a metal without conductivity? If you look at the moon, Titan there. So we will talk about the moons. Yes, we will talk about the moons in just a bit. So metals are because of the delocalized electrons, sometimes they're called conduction electrons. They're going to have that conductivity feature, Crazy Paul. So characteristic properties of a metal are therefore, because it's basically the positive ions forming the lattice-like structure, having the delocalized electrons not really bound to, atomic nucleus or neutral atoms, more like they're just there. So the electrons are therefore able to kind of float or flow more freely, giving it the property of having, property of being able to conduct electricity well. But they're typically reflective. They're typically good conductors of heat as well as good conductors of electricity. Yeah, maybe. I don't know. I'm just talking about the natural environments of Jupiter and Saturn. Both Jupiter and Saturn have high enough interior pressures to have layers of liquid metallic hydrogen. However, Jupiter, with its higher central pressure, has a much greater amount. So basically, both of them are huge interior pressure, but Jupiter does have more. But they're able to have layers of liquid metallic hydrogen at the center. However, because Jupiter has more central pressure, it has even more. So again, layers of liquid metallic hydrogen. How interesting. Yes, the freely the relatively free electrons within a metal is what is making it conductive. Yes, that's within the those delocalized electrons is in the definition of a metal. So I can show you the radial structure of all 4 Jovian planets here as well. But based on these detailed solutions of the hydrostatic equilibrium equation, combined with the knowledge of their chemical composition, we're basically thinking that Jupiter, so I'm looking at the picture here, Jupiter has a little bit of rock, a little bit of ice, a lot of metallic hydrogen, and then molecular hydrogen is basically the makeup of Jupiter. Saturn, again, has a little bit of rock, a little bit of ice, some metallic hydrogen, not as much as Jupiter, and then molecular hydrogen. We will get a preview of Uranus and Neptune as well. It's basically rock, ice, and molecular hydrogen. There isn't that metallic hydrogen layer. And then same thing with Neptune, rock, ice, and molecular hydrogen are the layers. So that's the radial structure of the Jovian planets. I can show you now. That's what this looks like. And you can see how Jupiter and Saturn are so much bigger. And once again, it's a little bit of rock, a little bit of ice, a lot of metallic hydrogen for Jupiter, followed by molecular hydrogen, a little bit of rock, a little bit of ice, some metallic hydrogen, and then molecular hydrogen for Saturn. Ice cream cones, yes. Exactly. So that's what we're dealing with in terms of the chemical composition. The Jovian planets are differentiated. So remember, we talked about differentiation when it came to our Earth, as well as all the other planets, basically. Chemical differentiation is where the heaviest stuff will sink to the center of a planet and the lighter stuff will float up. Makes sense, right? So our crust is like the Earth. Our core has iron. Heavy stuff has sunk to the center of the planet, and pretty much it's lighter and lighter above it. Just think about something like sand. It's very much more lighter than very dense iron. My dad used to get ice cream cones. Oh my gosh. Oh, that's not... Dr. C.S., can you be a little bit nicer to Mac tonight? Poor guy. Oh my gosh. I made the mistake of looking at a hidden message. You guys are brutal. Brutalia, Italia. Kidding, just kidding. So the Jovian planets are very differentiated. As we just saw, those ice cream cones told us that the inside, little bit of rock, compared to the rest, that is. I'm not saying that the rock is very little, but basically in the ice cream cone, we have rock, ice, metallic hydrogen, and then molecular hydrogen. And the metallic hydrogen part is enormous for Jupiter, because again, Jupiter really is a very unique planet amongst all the planets, amongst the Jovian planets. Its size, its mass, just incredibly bigger and very different. Central pressure, therefore very different. The Jovian planets are differentiated with a low density layer of hydrogen and helium on top of a medium density layer of ices, which is, by the way, ice here is not just water ice, but also ammonia and methane. So the ices we speak of with these Jovian planets, yes, exactly. Ooh, so the ice cream cone thing was actually true. So it is ice. There is ice in the ice cream cone. So the Jovian planets are differentiated with a low density layer of hydrogen and helium on top of a medium density layer of ices, which of course the ices are made of water, ammonia, methane, which in turn lies on top of a dense rocky core. So there is, all of this pressure is going to make some rock, right? So it's like, just like we have rock, we have a metallic core. So remember, so does Mercury. Even though Mercury is very tiny and we think it might have been bigger earlier, etc., and maybe it lost part of its mantle because it has a very large iron core. Especially with these massive, with anything massive, like a planet-sized, ball of mass, especially if you're not doing any nuclear physics, and especially if you're allowed to do cooling, if you cool down, in the middle, it's likely that under all that pressure, you're going to make some rock. So that's not so surprising. And also, the rock ends up in the center because of that differentiation thing, which is that the heaviest stuff will kind of shift to the center. So we have water, ammonia, and methane, which in turn lies on top of a dense rocky core. So there's a little footnote, since each Jovian planet has a rocky core several thousand kilometers in radius. So this rocky core, when I was showing you the ice cream cones and I was saying a little bit of, it's really in comparison, right? This little bit of rock is still a lot. It's just there's so much more of the metallic hydrogen layer in the case of Jupiter, and then on top of that, the molecular hydrogen, again, a huge layer. And in the case of Saturn, that metallic hydrogen layer is smaller, but still there. So since each Jovian planet has a rocky core several thousand kilometers in radius, we might say that inside every Jovian planet is a terrestrial planet screaming to be let out. So even though the rocky core of these Jovian planets is very small compared to the other layers, especially in the case of Jupiter and Saturn, which are the tremendously bigger and kind of different in their own category type of Jovian planets. But the rocky core is still very big and thousands of kilometers in radius compared to, of course, the rocky planet, the terrestrial planets or the rocky planets such as Earth, Mars, Venus, Mercury. So these rocky cores are almost like an Earth or a different rocky planet screaming to be let out of something gigantic like Jupiter with all that ice and metallic hydrogen and molecular hydrogen layers on top of that rocky core. So it's almost hard to imagine, but it's almost like if we had an Earth and then all these different layers on top pushing us down and can't get out type of thing. So Uranus and Neptune each have a mean density roughly twice that of Saturn. And so let me see that. Uranus and Neptune each have a mean density roughly twice that of Saturn and a radius roughly half that of Saturn. Thus, we expect the central pressure of Uranus and Neptune to be comparable to that of Saturn. So these are estimates, but basically Uranus and Neptune, again, each have a mean density roughly twice that of Saturn and a radius roughly half that of Saturn. Thus, we expect the central pressure of Uranus and Neptune from the math of that earlier page we were on to be comparable to that of Saturn. However, the hydrogen-rich outer layers of Uranus and Neptune are relatively thin. So those molecular hydrogen layers on top of the ice cream cone are much smaller for Uranus and Neptune. Even at their base, the pressure is not high enough for the hydrogen to take its metallic form. So because they're smaller and there's not as much of that pressure that we found to be the case with Jupiter and Saturn, they don't really have that metallic hydrogen layer in the case of Uranus and Neptune. Jupiter and Saturn radiate more energy than they absorb in the form of sunlight. Oh my gosh, wow. Isn't that so interesting? Yeah, somebody said that Jupiter is kind of like another sun. Well, here you go. Jupiter and Saturn radiate more energy than they absorb in the form of sunlight. For example, the rate at which Jupiter absorbs energy from sunlight is 3.8 times 10 to the 17 watts. There's an equation, I will skip that for now, but keep this number in mind. It's 3.8 times 10 to the 17 watts. However, observations at infrared We will talk about it. However, observations at infrared wavelengths reveal that Jupiter radiates energy at twice this rate. Obviously, Jupiter must have an additional source of energy. So, what is that? Any guesses what it could be? Yeah, Stephen said earlier that Jupiter is considered a failed sun. We will see why, so tell me this, Stephen. In order to be considered a star, so sun is a star, what are some of the basic things you require in order to be a star? We're talking about planets now, and we've talked about planets for a few lives, but before that, remember, we talked a lot about the stars. So what are the basic things that a star has to do in order to be considered a star? A star has to be like you. Oh, thank you. Hello, I am Batman. I'm not even that smart. Thank you. So a star, and the clue is, by the way, we talked about no. So no, it's not as difficult. It's actually simple, Stephen. So remember, so what is our sun doing? And also remember, when a star dies, a stellar remnant is one of three things: white dwarf, neutron star, black hole. And remember what happens to make a star die? What happens? There will be an explosion, correct? I'm Batman said explosion. Yes. When a star is dying, it explodes. Sometimes that is called a supernova, or even a hypernova if it's a very big supernova. But why will it runs out of, yes, it runs out of nuclear power. So basically, exactly. So it doesn't have to be hydrogen, because if it can burn other things, then it can do that as well for stars that are burning other things to make even more heavier elements. But yes, absolutely. So a star is gonna die due to a collapse, which leads to an explosion, which may be called a supernova. So those are the details of a star's death. But the main reason why a star will die is when it runs out of nuclear power. If it's not burning things to make other heavier elements, because it's supported by, those interactions are supported by nuclear physics, if it stops doing that enough, then it collapses under its own gravitation, and that collapse basically leads to these massive explosions, and you might get a supernova, and the star will die. And the stellar remnant, of course, depending on the star's mass, could either be a white dwarf or a neutron star or a black hole, which are all examples of dead stars, or the death remnant of a star. Its own gravity will kill the stars. Exactly. Its own gravity will kill the stars. So that means for something to be considered a star, like our sun, if you're calling something a failed sun, that is star-like, right? But what does our sun do? Why didn't we call Jupiter a star, right? What does our sun do particularly that it's a sun, or it's considered a star, which maybe Jupiter doesn't do? We will see what Jupiter does. But the most important thing that the sun does is, of course, it's burning. It's converting hydrogen to helium. It's doing a bunch of nuclear physics, and that's how it is burning, and it is radiating, and all this energy is coming out of the sun, and that's how we're alive. We get heat and light from the sun because of its nuclear power, because it converts hydrogen to helium. It is burning hydrogen and making helium. So if our sun stops doing that, and yes, that's true. We will get into that. If our sun stops doing that because it runs out of that power, then we will actually be in trouble. So now we'll read about what Jupiter does, because Jupiter is also very interesting. So if you're interested in the elements and the origin of elements, I actually talk about that in my live called, I believe I called it Big Bang Nucleosynthesis. And we talked about what were the elements that were made in the Big Bang of the universe. So what did the universe kind of start with? It was mainly hydrogen and a little bit of helium and trace amounts of lithium that started off in the early universe. And then every element heavier than that is made in stars. Okay? That's how we get elements in the universe. Okay, I am Batman. So, yes. So many lives ago, if you go back, if you want, after this live or whenever, if you go back to my channel and live tab, if you keep looking, scroll down and try to find the live called Big Bang Nucleosynthesis. Basically, it's a very important question you just asked, which is that how, basically you're asking about the origin of elements. And the origin of elements is definitely, one of the top questions even right now, because of course we have a lot of elements, but some of them are still mysterious because their exact process in which they're formed is still an open question, such as, for example, something like molybdenum, which is atomic number 42. But we do know from cosmology, which is also a topic that I've covered on this channel, that when the universe was formed from the Big Bang and in the early universe, so soon after the Big Bang, we actually mainly just had hydrogen, which is, by the way, the most abundant element in the universe is still hydrogen. And we had a little bit of helium at that time, and then we had trace amounts of lithium. So we didn't have enough helium. So by the way, all of the heavier elements can come from basically taking the lighter elements and doing nuclear physics things with them to make the heavier elements. Because the heavier elements, it just means the nucleus is getting heavier and heavier. To make a unique element, you would have to have a different number of protons in the nucleus, right? So it all has to do with nuclear physics. Right? So, so it all has to do with nuclear physics. Now, when the universe was getting started, hi, Sachi Mama. Sachi Mama is having a lot of zoomies. When the universe was getting started, there wasn't enough helium, for example, to take a bunch of helium nuclei and make something like carbon. So for that, the first stars were made, the first generation of stars, and pretty much stars are the thing that does nuclear physics enough to make the heavier and heavier elements, and that's how we get all the elements, and that's how we're made. We're all made from stardust, because once again, when the star has made these elements and then the star ultimately will die, it spews a lot of stuff everywhere into the interstellar medium, and we get gases, and we get, all this stuff just kind of spreads out. And for example, even us, right? We came from a gigantic gas cloud in our galaxy that ultimately condensated enough to make our sun, as well as our planets, including the Earth. We are stardust, exactly. So that's the whole story. We absolutely do need stars to make the heavier elements. Pretty much anything above helium, you need stars for that. Okay, and our own sun is making helium from hydrogen. It's the main thing that it does. And that's how we are still alive, because we get heat and light from the sun because of this exact interaction. And this nuclear physics step that it's constantly doing now for a while. About time you start saying. That's smart. So are we really made of the four main ingredients in the world? Are we really made of the four main ingredients in the world? So what do you mean by that? I'm not yes, Carl Sagan said we're made of star stuff. I think people like Carl Sagan, Neil deGrasse Tyson, these people have talked about these types of topics as well. We're made of carbon. So we are made of carbon. We know how carbon is made. Take some helium nuclei, and you can make carbon from that. Of course, we know that can be made in stars quite easily. And then we also are made of a lot of water. If you're asking about biology, I'm not a huge expert on it, but pretty much as far as I know, we're made of course, a ton of water, and carbon is a big one, big important element for our organic stuff, including life like us. And one very special thing about Earth, of course, is that it has liquid water. So that's tremendously important for life. And liquid water is, of course, just H2O. You need hydrogen and oxygen for that. And there's ways to make oxygen and carbon pretty easily in stars. But we should thank the stars and the fact that they died in order to make us. So nitrogen is more of an important element on Earth. If you're considering the universe, so our Earth is a very tiny part of the universe. If you're considering the entire universe, the most abundant and most important element is actually just hydrogen. Okay, everything else is much less than hydrogen. So in the overall universe, the most abundant element is hydrogen. Earth does have these other things that you're talking about. Of course, silicon is a big one on Earth as well. Nitrogen, So Earth is very special, and Earth has more things and more elements and different sort of composition than even some of the other planets in our own solar system. But overall, if you're asking about the universe, that's more of a cosmology topic, which I've covered in the past and I will cover again because I think that's a very interesting topic, which has to do more with the universe. So consider this to be more of an astronomy chat, because really considering something as specific as planets or even our solar system is very much an astronomy topic and not a overall big picture cosmology topic. So we do cover cosmology as well on the live, though. We have covered it in the past where we talked about the entire universe as a whole. It's much more zoomed out. And in that particular type of way, it would be hydrogen that is the most abundant element in the universe and what is basically important. Then carbon and nitrogen, those things are not as important in the universe. We have metals in us that only form in the stars. So yes, everything in astronomy, everything above helium is considered a metal. But yes, iron, again, those things are all made in stars. You absolutely need stars to make everything above helium, and even helium is made in stars. For example, our own sun. Do you ever wonder if there's a cosmic consciousness experiencing itself? Or do you feel like it's more probable than not we are in a machine or both? We are ants living in the ant farm. Oh, thanks for clarifying. So I was mistaken, but we are stardust? Yes, we are stardust. Indeed. You were mistaken. Yes, we are stardust. Everything we're made of, other than hydrogen, which of course is a part of water, H2O, but to make H2O, you need the O, right, which is oxygen. Everything other than hydrogen is made in stars. So like I said, in the beginning of the universe, you had hydrogen and a little bit of helium. So You could say that maybe helium, you kind of get it without stars too, but pretty much, especially everything above helium, which is the majority of the periodic table: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. That's the periodic table up to 20. 21 is scandium. Uh, all the elements above hydrogen and helium, especially above helium, are made in stars, every single one of them. So, like your name, thank you. So yes, we absolutely are stardust. We are absolutely star stuff. The stuff we're made of was made in stars, and then those stars had to probably die. Not just probably, definitely died. And basically you'll see when we talked about supernova and stars dying. If you another live I will point you to, if you're interested, is the, I believe there's a, sometimes I'll name the lives something random and not specific, but I think I do have a live called Stellar Remnants. If you go into my live tab and look at the scroll down, and in the stellar remnants live, we talked about stars dying and exploding and making a supernova. The thing with stars' death is also kind of dramatic, right? So stars could die quietly and then all the stuff wouldn't go everywhere, right? But because stars die so explosively, and supernova is basically the name of an explosion, right? It's an explosive death because there's so much mass involved, so much drama, pain, and everything involved in the death of a star. As it collapses under gravity, there could be shocks happening within that material and explosions and all that. That actually leads, and there's also stellar winds. There's ways for that material to kind of get off of the star and be carried away with all this energy and momentum. And the explosion basically leads to everything spewing everywhere, and that's how, and ultimately contributing to the richness. Look at this, Suji is having huge zoomies. The explosion is why everything goes everywhere and contributes to the richness of gas and interstellar gas in different galaxies and such. And those are the types of big gas clouds that then ultimately condensate. And again, it depends, on the exact circumstances. Our sun also is a condensate from such a system. And then depending on which planetesimal leading to the planet that you are, for us it's Earth, then you get the proper surroundings for something like life, such as what we have. Yes, so indeed, this is a miracle that we are here. We should be very thankful. Thank you, universe, for giving us the opportunity to be here on Earth and be alive, and also be on this live. Thank you so much. Welcome, welcome. So God's space is beautiful. Yes, made of stardust sounds way better than made of the. Yes, well, we're not made of dead bodies of stars. We are made of star dust, I would say, because it's the star stuff going everywhere. And star dead bodies are more the stellar remnants, which is the remnant or the part that's left behind where the star was. So that's more of the star dead body, which is either the white dwarf or the neutron star or the black hole. So we're not. Actually, we might be a little bit made of the star dead bodies too, but that's another whole discussion. Gosh, both Batman. Okay, do you know what Annie Frank? What? Okay. Do you think consciousness can be an inherent property of energy? A miracle. Okay, let me finish reading about Jupiter or discussing Jupiter. So, obviously, Jupiter must have an additional source of energy. So, we know that Jupiter's rate of energy output is bigger. So, what is it? As we've seen in the case of Earth, radioactive decay of unstable elements is one source of internal heating. So, one source of internal heating is radioactive decay. I think it's just Reese here. Yeah. It's okay, Reese. Let them be. I mean, we can just chill because I know it's a lot of work to constantly be modding. So, as we've seen in the case of Earth, radioactive decay. So, we actually did not cover this part yet. But basically, radioactive decay of unstable elements is one source of internal heating. That makes sense. However, the rate at which the Earth is heated by radioactive decay is only 2 times 10 to the 13 watts, a factor of 5,000 lower than the rate 10 to the 17 watts at which it absorbs solar energy. Doro is on travel, so he said he will not be here. Ooh, you missed Doro. He said he will not be here. But I support that people bother him. So, anyway, so radioactive decay, the rate at which the Earth is heated by radioactive decay is only 2 times 10 to the 13 watts, a factor of 5,000 lower than the rate of 10 to the 17 watts at which it absorbs solar energy. Even scaling upward by Jupiter's mass, which is 318 m Earth, and ignoring the fact that Jupiter is relatively low in heavy, unstable nuclei, radioactivity falls short of explaining the total energy radiated by Jupiter. So the first thought was that it could be radioactivity. Maybe there is unstable things that are decaying and producing energy within Jupiter, but we did some thought about that. In Jupiter and Saturn as well, heat is generated by the global contraction of the planet. Again, let's make the simplifying assumption that a planet has constant mass density of rho bar. Consider a spherical shell centered on the planet's center with radius small r and thickness dr. The gravitational potential energy of the mass shell is du equal to minus g mr over r dm, where mr we saw is 4 pi over 3 r squared rho bar, is the mass enclosed within the shell. So we were kind of doing this to compute the central pressure a bit ago. And dm is 4 pi r squared rho bar dr. That's the mass of the shell itself. Thus the potential energy of the shell can be written in the form of du equal to minus 3g all brackets 4 pi rho bar over 3 squared r to the 4 dr. So there's some relation basically with all of the gravitation stuff and this potential energy. The potential energy of a planet with radius r is obtained by integrating over all the shells from r equal to 0 to r equal to big R, which is the big radius of the planet. So you basically get U, which is the potential energy now, because we know what du is because of that shell. Now we're going to integrate over all the shells, and eventually we get minus 3 over 5 big G m squared over r. By decreasing the radius r of the planet while keeping its mass constant, because you could, we can decrease the gravitational potential energy u by du dt. So now we're taking a derivative of this potential energy with respect to time as a function of time. Then you get basically m would be constant. The big R is constant, but maybe the part that you're changing with time, that part can be taken, you could take a derivative of that. So you would get 3/5 gm squared over r squared comes out, and then dr dt. So basically we're trying to solve for the contraction rate of the planet. We know the mass, the radius, we can take integrals to get the potential energy, and then ultimately we want how this potential energy is changing. So solving for the contraction rate of the planet, we find that dr dt as a, now dr dt is on the left hand side, we get 5/3 du dt r squared over gm squared. If Jupiter's excess radiation, so it's almost like we do all this math and then we compare Jupiter with the other planets, knowing that its mass is so much different than the others. So if Jupiter's excess radiation is around 4 times 10 to the 17 watts, comes from gravitational potential energy, then Jupiter must be contracting at the rate of, plugging it all in, around minus 1.6 times 10 to the negative 11 meters per second, which is around minus 500 kilometers per gigayear. So let me say that again. So it's minus, because it's a contraction, 1.6 times 10 to the negative 11 meters per second, or minus 500 kilometers per gigayear. Because the meters per second is it's a very small number in meters per second. So if you consider it in kilometers per gigayear, then it's a little bit better. So during the lifetime of the solar system, which is around 4.6 gigayears, Jupiter need only have contracted by around delta R of around 2,300 kilometers. So not a whole lot. Basically, this contraction could have happened because basically 4.6 gigayears, we're only 4.6 gigayears old. So Jupiter need only have contracted around 2,300 kilometers, about 3% of its current radius, in order to maintain radiation at its current rate. So it's such an interesting thing because it's so huge and it could be contracting, releasing this potential energy. You get this radiation. Depending on its radiation, we're like, okay, let's do the math. What kind of contraction could it have done? And it's not like a very shocking level of contraction. Basically, over the course of our entire lifetime of this solar system of 4.6 gigayears, it could have contracted around 2,300 kilometers, which is nothing for the delta R, that is, which is nothing for Jupiter, and it would have maintained its radiation at its current rate if it did that. Yes, we think so. So it's probably a combination of this contraction, and also it could be there could be the radioactive decay. But we think that the radioactive decay is probably not contributing to most of it. Yes, we are 4.6 gigayears old. The appearance of Jupiter and Saturn depends on the temperature and the resulting chemistry at the highest levels in their atmosphere. So basically, the first thought that we had, so yeah, I'll just recap. The first thought that we had was, is it a bunch of radioactive decay that's happening? but we kind of thought about it in terms of our own planet's radioactive decay. And we saw that the rate at which our Earth, for example, let me read this sentence again. The rate at which the Earth is heated by radioactive decay is only a factor of 5,000 lower than the rate at which it absorbs solar energy. So the fact that Jupiter was emitting energy, that's the weird one. So even scaling upward by Jupiter's mass and ignoring the fact that Jupiter is relatively low in heavy unstable nuclei, radioactivity falls short of explaining the total energy radiated by Jupiter. So it's about kind of like taking our radioactivity and comparing, like scaling by mass and saying that Jupiter, even if it did that, it doesn't really explain the radiation we're seeing from Jupiter. But I think pretty much it's a thought that it very well could be doing a global contraction. So in Jupiter and Saturn as well, heat is generated by the global contraction of the planet. And then we did all this math to get the potential energy stuff going. And we saw that it's actually not crazy to think that it could have been contracting a little bit. And even from that contraction, because of these planets' enormous mass involved, you would actually get that potential energy release in terms of the contraction, releasing all that radiation. So now we will think about, now we're going over to the appearance of Jupiter and Saturn. Yay! I get drunk on physics. You guys are such good friends with each other. I love it. So now appearance of Jupiter and Saturn are also going to kind of depend on pretty much temperature and the resulting chemistry at the highest levels in their atmosphere, because we're not really that close to Jupiter and Saturn. So these types of things like temperature and chemistry is what's really giving us their appearance. So the rapid rotation of Jupiter and Saturn stretches clouds into bands that run parallel to the equator. Good night. So if you were wondering why there's these bands, well, there is the rapid, crazy rapid rotation of Jupiter and Saturn stretches clouds into bands that run parallel to their equators. The banded structure is most clearly seen in the case of Jupiter. So I'll show you the picture in just a second. However, Saturn shows bands. Oh, they're prettier. Well, they're kind of pretty with Jupiter too. Saturn shows bands parallel to its equator as well. So there's these bands on the planet because of the rotation. So we're going to show you the picture of Jupiter and Saturn with the ring of Saturn removed, because the Saturn ring is a distraction at this time. We will talk about the ring later. In the case of Jupiter, the visible clouds are primarily in 3 layers that are around 75 kilometers deep. Ooh, that's cool. The uppermost layer consists of ammonia, that's NH3 crystals. In the middle layer, we have ammonia and hydrogen sulfide, that is H2S, combined to form crystals of ammonium hydrosulfide, NH4SH. In the lower level, the clouds are made of water crystals. All of these substances are white in their crystallized form, the varied colors visible in the figure we're about to show are the result of the complex chemistry of trace constituents in the clouds. So there is some chemistry happening which gives us the color because those crystals are white. In the case of Saturn, which is less than a third the mass of Jupiter, so Saturn is a lot smaller than Jupiter, but still pretty massive. Again, the Saturn mass is 95 m Earth, whereas Jupiter is 318 m Earth. So in the case of Saturn, which is less than a third the mass of Jupiter, the lower gravity spreads the 3 cloud layers over a greater range in radius, about 300 kilometers. So it's spread out a bit more. The increased optical depth of the cloud layers makes the lower layers appear somewhat hazy, and accounts for the more muted colors of Saturn when compared to Jupiter. So Uranus is 14.5 m Earth. So now you can look at the pictures, okay? Here's Jupiter. Here's Jupiter and Saturn with Saturn's rings removed for now because we're just comparing the bands on Jupiter and Saturn, okay? Here we go. Jupiter is on top. You guys know that there's more things going on, or more of a more dramatic banding in Jupiter, right? Yeah, color printing is more costly. I think that they were trying to prevent or mitigate the cost, maybe. If you're my teacher. So, Jupiter has more mass. It's rapidly rotating. Has more gravity, and so its banding is more dramatic. Saturn kind of spreads it out over 300 kilometers. The upper atmosphere of Jupiter is divided into zones and belts. So excuse me, what? Ooh, also, can you guys please subscribe and like and share? Please like, share, subscribe, and yeah, it would be great to have more likes today. If you could instantly visit any planet for 1 hour and be completely safe, which would you choose? I'd go for big boy Saturn. Yeah. Yes, I mean, Saturn's looking pretty good right now. More stable-ish. Not as big as Jupiter. And I guess you would get all that. Well, yeah, Saturn's kind of closer to Jupiter than anyone else. So the upper atmosphere of Jupiter is divided into zones and belts. The zones are the lighter colored bands that we just saw. They're lower in temperature and higher in altitude than the belts and represent the tops of high pressure clouds that are rising upward. I don't know. I don't know about the Saturn thing. Maybe. I think so. Shani, Shanivar. Yeah, I think it is. In Sanskrit, Saturday is Shani, and that is also the planet Saturn, I believe. So, yes, I think so, but I don't know exactly. More of an history question, maybe. So, maybe we will see that here. So, the zones are the lighter colored bands, and they're lower in temperature and higher in altitude than the belts and represent the tops of high pressure clouds that are rising upward. Named after a Roman god who named Saturday then. I heard Saturn had okay. The red spot. So I think now we can get to the red spot that Stephen has been so patiently waiting for. So now that we've looked at the pictures of Jupiter and Saturn, now that we've looked at the pictures of Jupiter and Saturn and we see all the banding, zones, belts, all that, basically now we talk about the red spot. So the red spot is a high pressure system in Jupiter's southern hemisphere. Yes, high pressure system in Jupiter's southern hemisphere. Thank you for liking and all that stuff. As air flows away from the center of the spot, it is deflected to the left by the Coriolis effect because, of course, it's rapidly rotating like crazy. As a result, the great red spot rotates counterclockwise. The great red spot was first recorded by astronomers on Earth in the mid 17th century. Yes! Careful observations of cloud motions reveal that the Jovian planets rotate differentially. For instance, Jupiter has a rotation period that is shorter at the equator than at the poles by approximately 1%. The extremely rapid rotation of Jupiter with a p rotation or a period of rotation of 9.8 hours, which is really rapid, and Saturn has a p rotation of 10.5 hours, combined with their relatively low density means that they are the most rotationally flattened of all the planets. Oh, the polar diameter of Jupiter is 6.5% shorter than its equatorial diameter. They're getting flattened by their rotation. For Saturn, the polar diameter is a whopping 10% shorter than its equatorial diameter. Yeah. By comparison, the polar flattening of the stiffer, more slowly spinning Earth is only 0.3%. So we have polar flattening too, but we're stiffer, we're more slowly spinning, 24 hours, right? Long enough. The polar flattening is only 0.3%. So all this crazy rotation, etc., of course, gives it very strong magnetic fields as well. For both Jupiter and Saturn, the field of Jupiter, thanks to its rapid rotation and thick layer of liquid metallic hydrogen, is exceptionally strong. At the top of Jupiter's cloud deck, the magnetic field strength is 5 times 10 to the negative 4 Tesla, or around 10 times B Earth. That is the 10 times the magnetic field of Earth. Yes, 10 times the magnetic field of Earth is what is the magnetic field on Jupiter. The magnetosphere of Jupiter has a radius of 200 R Jupiter. If it could be seen by human eyes, it would loom in the Earth's sky as large as the full moon. Oh wow. So if you imagined this magnetosphere of Jupiter, which has a radius of around 200 the radius of Jupiter, and if we could see it, then it would loom in our sky as large as a full moon. Wow. Charged particles, because Jupiter, I mean, we can see Jupiter pretty well, like, depending on time of year, and it would be really big. Charged particles released by eruptions on Jupiter's volcanic, make sure my nose is, charged particles released by eruptions on Jupiter's volcanic satellite Io, this is one of the satellites or moons of Jupiter, are trapped by Jupiter's magnetic field into a torus around Jupiter. So we will talk about it more, but basically say you have something going on a moon of Jupiter, like a volcano on its moon. Well, the charged particles are going to get trapped by the magnetic field of Jupiter because it's such a strong magnetic field. So that also affects things and changes things around Jupiter. Big visible moon, yeah. This torus of charged particles is a strong source of radio emission. So as we know, charged particles, when they're trapped, remember we talked about how black holes can sometimes accrete material from a nearby star or something like that. And all those accreting, falling particles can be a source of radio emission, radio waves, basically. So same thing kind of here on a different scale. These are the charged particles coming out of maybe a moon of Jupiter, falling into the magnetic field of Jupiter and making this torus around Jupiter. And that thing is now a strong source of radio emission. So we're going to next talk about cyclotron frequency, cyclotron radiation. That stuff will be the next part. I need to charge my phone. It's about to die, actually. So 1 second. We might... Oh, hi, Suchi. We might save the cyclotron radiation for next time. And keep chatting in general at this time. But I think we made good progress on Jupiter today. Just want to make sure it is actually charging. Yes. Hello. There is. Do you see Suji? Yeah. Hi, Suji. Okay. Io is the innermost big visible moon of Jupiter. Steven Spears says, need to go to sleep. Where's Baji? Baji! Sachi! When I'm calling Baji, Sachi's the one who's responding. I think she wants attention. Good night, Steven. So the next part that we're about to cover for Jupiter is going to be the cyclotron radiation. So because Jupiter has an insanely strong magnetic field because of its rapid rotation, etc., we will actually see how that affects certain things. And so electrons in a magnetic field of strength B will spiral in a helix with radius equal to the Larmor radius. So who can say what this type of phenomena is called? And that will be the next topic. And also, who can say what is the radiation produced by relativistic electrons in a magnetic field? What is that called? we have talked about this before. So there's going to be a couple different types of radiations that we'll talk about now next in the next part of this. And then we will move on to the moons of Jupiter and Saturn. I think we'll do that the next time. We definitely want Stephen to catch that. So we will do that next time. In the meantime, if people could please like the live, that would be amazing. That we could get a few more likes, and certainly we will continue to talk about the moons of Jupiter and Saturn, as well as what the magnetic field of Jupiter does. Ooh, and also what we'll do is I will rotate and let you see the book that we're using. So that it gets the recognition that it deserves. And welcome to the live. If you're joining, you can rewind and listen to our discussion that we've been having about the Jovian planets. We've covered a lot about Jupiter and Saturn mainly today. And we're on the part where we're about to kind of talk about the magnetic field of Jupiter and its moons and things like that going forward. We'll pick up next time. But if you're here, welcome to the live, and please rewind and see the full discussion that we had. Thank you so much, and good night to Stephen. And thank you everybody for being here and supporting the live stream and chatting and sending all your messages today. Hi, Soji Mama. Jovian planet means Jupiter-like. So Jupiter is Jovian, and basically the planets from Jupiter, Saturn, Uranus, and Neptune are called Jovian planets. Okay. Thank you. Good night. Sachi Mama really wants some foodie. Thank you, everybody. Chat has been batshit tonight. Oh, really? So I actually did not see everybody's comments today. I think I was trying to focus, and so I didn't see everybody's comments today. I think, thank you for chatting with everyone. That was good. I think people like when they're, being acknowledged and stuff. So that's good. Thank you guys. Yeah. Where are we? Here. That's good. Put it right there. No. See you. See you tomorrow, Ben. Thank you. See you tomorrow. Indeed. I'll still hang out for a bit, but yeah. I think everybody was there was a lot of chatter. I didn't catch everything. What was the main theme? What were people saying, Reese? Yes, that's what I figured, that they were kind of arguing a lot today. Yes, your arguments were on topic, for sure. Sort of on topic indeed. So like those are helpful because it keeps the chat sort of coherent. But today there was arguing about just like random things, like anything and everything, right? Jovian planets plus kitties. Yeah. Got any plans for tomorrow? Just usual stuff, work and this and let's see. I want to go to the gym tomorrow for sure. Do some swimming, eat some foods. I made some rice today, so hopefully I can eat that tomorrow. Just the normal. Yes, I do go for walks. It's January, it's a little cold, but if it's sunny, then generally speaking, I go for a walk. Yeah. I can hear you though. Okay. Thank you. Oh yeah, Reese, by the way. Remember about the bakery? Yep. That whole bakery situation is completely done. Yeah, yep. There was some more drama with that, but it's done now. Thank God. So yeah. More drama. What do you mean by more drama? Well. Tell. More drama. So, let's just say that I'm extremely croissant-less these days. Like, I can't really get my croissants anymore. But I am glad. It's all good. It's all fine and good. Yup. Mm. He didn't like the lives. He was at the lives. One of the lives that you were asking about this topic, he was there. It's kind of toxic. Oh, wait. Why am I removing this? It was a little scary, a little stalkerish. No worries. But yeah, he's like there and listening and coming, and well, there were many things, but he was unhappy with the lives as well. Oh yeah, no, that was fine. It's just we couldn't have gone into like detail on it. You know what I mean? I don't think he got it. Like, yeah. I don't think he understood the material. And I think he thought that the lives were kind of pointless, and yeah, didn't really get this job, basically. But I think like it was like none at all for him. Nothing about this was anything comprehended. No, definitely not. Pastries, pastries. I think I like the pastries. My friends have banned me from eating pastries now. It was whatever. Short-lived connection, it's all done. Good. Back to senses. But yeah, that's yeah. Sometimes like earlier when this was coming up and you mentioned it, like they would like literally be in the chat. You know what I mean? So that's why I'm saying it now, and then we won't have to like mention it again. It was just kind of creepy. carpenter and bricklayer, and she has the doing of her house, and then gets rid. Are you serious? That's what you think it is? But yeah, we should give it a code name in case it comes up and I can just signal that we cannot talk about it. Maybe we'll just say bakery not. Okay. Well, now you know. All right, everybody. Thank you so much for being here. See you guys next time. Okay, fine.